Okay, we're going to talk about section 3.1, predicates and quantified statements. Consider the statement x is greater than 10. Is it true or false? Well, it depends upon what x is. It's true if x is 13.27, and it's false if x equals 3.14159. A sentence like x greater than 10, x is greater than 10 is called a predicate. It has one or more variables in it, and it becomes a statement that can be true or false when you have specific values for the variables. So by itself, x greater than 10 is neither true nor false. It's only when you say what x is that it becomes a statement. A predicate can have more than one variable, and the variables needn't be numbers. So, for example, x and y are married to each other. That's a predicate. It's true if x equals me and y is Victoria, my wife. It's false if x equals Angela Merkel and y equals Boris Johnson. The set of possible values for a predicate is called its domain, and the set of values in the domain which makes it true is called its truth set. Quantifiers combine with predicates to make statements. So suppose the domain for each of the predicates below is the set of all real numbers. For each of these is now a statement because of the quantifier for all or there exists. So for all x squared is greater than or equal to 0. That now is a statement. It's either true for all x or it's not true for all x. There exists an x such that x squared equals 2. Again, that's a statement. Either there does exist such an x or there doesn't. So for all is what's called a universal quantifier. It means something is true all the time. And there exists is called an existential quantifier. It means there exists at least one element which makes the statement true. Another example, for all x cubed greater than x, and there exists x such that x to the fourth equals negative 1. So these are each now statements that could be either true or false. Which of the above are true and which are false? Well, x squared greater than or equal to 0 for all x is true. When you take a real number, x squared is greater than or equal to 0. There exists an x such that x squared equals 2 is true. X equals the square root of 2 or negative square root of 2. Either one will make that statement true. For all x cubed greater than x is false. For example, if x is 1/2, then 1/2 cubed is not greater than 1/2. There exists an x such that x to the fourth equals negative 1. That's also false, because if you take any real number and raise it to the fourth power, you get a positive. Okay. The symbols that we use, because mathematicians are lazy and don't like to write out words, so the upside down A means for all, and the backwards E means there exists. So the four statements we just looked at would now look like this in symbol form. Okay, now it's your turn. Consider the following statement. For all basketball players X is tall. Which of the following are equivalent ways of expressing this statement? Pause the video now and go through each of those statements. Is it equivalent to the statement above, for all basketball players X is tall? Pause the video and go through it. Hopefully you realize that A, E, and F were equivalent and the others are not. So every basketball player is tall. That's the same as saying for all basketball players X is tall. But in B, some are tall. Well, no, it's for all. Okay. And D, anyone who is tall is a basketball player. That's got the order wrong. It's not that all tall people are basketball players. It's all basketball players are tall. So hopefully you got these. How about this one? Let D be the set of all students at your school, and let M of S be S as a math major, C of S as a computer science major, and E of S as an engineering major. Express each of the following statements using quantifiers, variables, and the predicates. So again, pause the video and see if you can do these. Pause the video now. Really, pause the video. Okay. So here's some of the answers. There exists S in D. So we haven't talked about this symbol before, but it means it's an element of, or in. So there exists a student in the set of all students at our school, such that S is an engineering student, an engineering major, and a math major. Or you could write it this way: there exists an S in D such that E of S and M of S. Every computer science student is an engineering student. For all S and D, if they're a computer science student, then they're an engineering student. So hopefully you can do these, and this is a short introduction to quantifiers and predicates.